The tech landscape is shifting. Software is moving from passive text generation to active, autonomous digital execution. When you type a prompt into a standard interface, you see a conversational reply. Beneath that surface, the model triggers complex software actions across multiple external systems, moving far beyond simple word prediction. A standard generative AI model cannot do this on its own. At its core, it is a highly capable reasoning engine trapped behind a static knowledge wall. It only knows what was in its training data up to a specific cutoff date. Because of that cutoff, the base model is completely blind to the live environment. If you ask it for current stock prices or updated flight schedules, it fails. It lacks the infrastructure to interact with external reality. To solve this, we must change the architecture. We are going to map the precise technical progression from a basic large language model to a specialized AI agent, and finally, to a fully autonomous agentic AI network. We will build this infrastructure from first principles. By isolating the exact computational layers added at each step, we can observe exactly how these systems gain their autonomy. Understanding the structural evolution is the only way to bridge the gap between predictive text and real-world software automation. We start with the baseline, generative AI. Conceptually, this is a standalone large language model operating entirely on pre-trained computational weights within a strictly isolated environment. This isolation enforces a hard limit. Any real-time information, represented by this live data stream, simply bounces off. The model cannot process information generated after its initial training phase. To cure this blindness, we introduce tools. By dissolving the boundary and detaching an external API, a database, or a web search function, we provide the architecture with a sensory organ. The system is now dynamic. The live data stream flows through the API directly into the model, allowing it to pull real-time context to answer immediate questions. For instance, if you ask for the price of a flight to New York, the base model has no answer. But equipped with a travel API, it queries the live pricing and feeds that exact number back into its reasoning engine. Giving an LLM tool access is the crucial first step in bridging the gap between passive knowledge retrieval and active data fetching. Fetching data is useful, but executing tasks requires a mechanism for autonomy. When we encapsulate the LLM and its tools inside a continuous, self-executing logic loop, we create an AI agent. The execution path starts with a specific goal from the user. That input strikes the LLM, which acts as the central router, determining which tool to use and sending the request outward. During the execution phase, the chosen tool queries the external server. It pulls raw data, such as 5 distinct flight options, and returns them to the LLM for comparison. The LLM processes the variables, isolates the optimal choice, and utilizes the API one last time to finalize the booking. It moves from analysis to actuation. However, this architecture has a ceiling. An AI agent operates within a rigid, single-domain objective. While an AI agent removes the human from the immediate execution loop, it is fragile. If a user introduces a constraint outside of its single assigned toolset, the logic loop breaks and the agent fails. Consider a highly complex prompt. Book a 7-day trip, ensure the weather is sunny, keep the total budget under $600, and verify my legal visa status before purchasing. A single narrow agent crashes immediately when processing this request. It possesses a flight API, but it lacks the cross-domain reasoning required to cross-reference weather patterns, financial limits, and legal documents simultaneously. The architectural solution to cross-domain constraints is Agentic AI. We deploy a networked system of multiple specialized agents that communicate with each other to achieve the complex overarching goal. In this parallel execution architecture, the flight agent begins its specific task. It simultaneously queries the travel and weather APIs to find a route that satisfies both the budget and the sunny itinerary constraint. Concurrently, the immigration agent handles its specialized domain. It securely accesses your personal OneDrive to parse your passport documents and verify your legal status. The defining capability of Agentic AI is cross-communication and failure retry logic. These agents actively monitor one another, serving as institutional checks and balances. If the immigration agent detects an expired visa, it sends an override command to the flight agent. It safely halts the entire workflow, completely preventing a financial transaction from occurring under invalid legal conditions. Autonomy requires the architectural reasoning to safely manage environmental failures and multi-step dependencies. This multi-agent architecture is entirely domain agnostic. By stripping away the travel context, we reveal the underlying node structure that can process any complex logic requirement. This exact same network structure powers complex enterprise operations, like human resources onboarding. A central orchestrator receives new hire data, triggering subagents to sequentially update the HR database, deploy the official welcome emails, and generate hardware tickets on the IT server. Software engineers formalize this architecture today using modern development frameworks like LangGraph, CrewAI, and Agno. These frameworks allow architects to define custom agents cleanly. They grant each agent specific access levels to memory, logic models, and tools, and establish the exact rules for how they communicate. We can map the complete technological hierarchy. Generative AI provides the reasoning. Simple AI agents execute narrow tasks. Agentic AI orchestrates the holistic strategy. Generative AI is the raw computational processor. Agentic AI represents the complete autonomous software systems built around it to accomplish the actual work.